Hello and welcome back to Calculus 1 section 4.6 on linear optimization and differentials. The first part of linear approximation is utilizing tangent line to compute function values that we don't want to compute or can't compute without a calculator. My question to you is, how much is the square root of 3? How much is the square root of 10? How much is the square root of 15? How much is ln 3? Right? How much is ln 10? And how do you compute these values without a calculator? And what is the process of approximating these things? If you understand that calculator has been around for 50 years at most, 40 years, right, around. Before that, engineers used to walk around with a book called log tables. That book only had values, tables inside. So for sine, cosine, ln, and so on. So you need, for your engineering calculation, you need ln of 23.7. You open the book and you flip through pages until you go and you find in the table ln of 27, and it gives you the decimal to whatever precision is in the book. Now, that was there because they did not have calculators or computers to compute those, so it's easy and convenient if you have those values in the book, and then as engineer you can flip the book. But where did the book come from? Was there a mathematician that went onto the mountain and then, obtained the book on these stone tablets and then carried it down and then...
It's an actual 10 cents.
Right? Where is the book coming from now? So tonight we are going to honor our ancestors and compute some of the values the way they used to compute these values, because they did not have calculators. And then the second part with differentials, which is going to do some word problems, is going to be awesome. All right? So linear approximation. We are talking about tangent line, compute square root of 10. Now, for the entire section of linear approximation, let me paint the picture. You're on a desert island. Your cell phone battery ran out. Your TI-84 or whatever battery ran out, because you never leave your home without that one, right? Wilson is gone.
No, Wilson!
And you need to calculate root 10 because you are building. So you don't have Anthony either. And he doesn't have himself. So you know that the square root function looks something like this. And then 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 eventually comes around. And you know that the exact value is right there. But you don't really know what it is. What you do know, however, is what square root of 9 is. And a square root of 9 is 3, yes. Here, you're on a desert island. And if you draw the tangent line, through this point. When you zoom in over here, you see that the y value of the tangent line computed at 10, which is the red line, is very close to the y value that you actually are looking for. You are looking for the black dot, and you can compute easily the red dot, which is right there at 10. So the goal of this is to find the closest value that you can compute without a calculator to the point of interest, and then find the tangent line at that point. Which means that the y values of the tangent line will be close enough to the original value that you are looking for. Does that make sense? So you are interested in this. Black line would be square root of 10. The red line would be some kind of linear calculation where you would have m times 10 plus some kind of b. And you know that when you calculate tangent line, you have m and b, right? So it's much easier to compute m times 10 plus b than to compute root 10. So that's what we're doing, right? So let's go and just find this tangent line at 9 and then compute the rest. So tangent line at 9. F of x is equal to root x, and my value a, special value, well, x, is 9, and then we'll compute, once we are done with tangent line, we are going to compute the rest. So, tangent line procedure, you had it on your exam, you're supposed to find the derivative, which is 1 over 2 root x, and then to calculate m, you take the derivative, calculate at the value you're interested in, so 1 over 2 times square root of 9, which is 1 over 6. So now you also need the y value, right? So y is f of 9, and that's going to be square root of 9, and that's 3. And you have everything. Y equal mx plus b. Your y value is 3. Your m value is 1 over 6. Your x value is 9 plus b. 9 and 6 will cancel. You'll get a 3 and a 2. So we have 3 minus 3 halves equals to b. b equals 3 halves. And your tangent line is y equal 1 over 6x plus 3 halves. Square root of 10 is approximated by computing y of 10 from the tangent line. So that is going to be 1 over 6 times 10 plus 3 halves. And this is something that you can do with a stick in the sand, right? And you will have approximation for square root of 10. So instead of computing in the square root, you are computing in the tangent line, which is this joke linear calculation. So you have your 10 divided by 6. Well, that's going to be, leave it as 10 over 6 plus 9 over 6, which is 19 over 6. So now you're going to do, again, remember, no calculators, desert island, just stick in the sand. 6 divided into 19. 6 into 19 goes 3 times, then 18. And then you subtract, there's a 1 there. Oops. You have a 1. And then when you add 0 out of nowhere, you put a decimal point. 6 into this goes once. 1 times 6 is 6. You get a 4. Put another 0. 6 into 40 goes, very good. That's 36. And then you get into this pattern of 6, 6, 6, right? So we're just going to put 66 always as a pattern. So we approximated root 10, right, to be 3.166, right, going on forever. You can call it 3.2, depending on...
That's what I said in the beginning.
Yes. And you can now, because, right, we can check, use the calculator for the square root of 10.
Found the batteries.
And the calculator is going to say that square root of 10 is approximately 3.16223. And you have 1.6, come on. Or really, third decimal, right? It's good enough. It's good enough. So, and we haven't done any square roots or anything, out of square root of 9, which is 3. So this method is really cool. You can also open your Thanksgiving, right, dinner conversations with one of these guys. Exactly, you start with that.
Son, that's great.
Check
I don't
this
know what
out.
this means.
Because eventually someone is going to say, what do you know? Well, I can calculate ln3 by hand. Let's go. So you can, yes, as soon as someone brings up like, what do you know, you green? Let's go.
Thanksgiving.
Yeah, it's coming up. I mean, 2 weeks. You will have opportunity to kind of practice this for the final. So ln3, what is the value close to 3 that we can take ln of? 2.7 blah blah. What's that value? E. So E is about 2.7. So that's close to 3. We can use that, right? So your job is to find the close, and that's the hardest part out of all of this. To find the value, because what if I want ln of 27, right? Now you have to go and figure out what you can do with the ln, e squared, e cubed, some combination of something somewhere, somehow, to come up with as close as possible to 27, right? So now my function is ln x. My derivative is 1 over x. The slope m is derivative computed at e, which is 1 over e. The y value is ln of e, which is 1. That gives me e1 as a point and slope of 1 over e. What is my tangent line? Well, y equal mx plus b. My y is 1. My m is 1 over e. My x is e plus b. These guys cancel, right? And I get b equals to 0. So the tangent line is y equals 1 over e times x. So you can just say x over e.
I thought the E canceled there.
Yeah,
And then that's how you calculate the b equals 0.
But now you're writing the tangent.
Now you're writing the tangent equation and your b is 0, so you don't write plus 0. So now you have your tangent equation, tangent line. So how much is ln of 3? ln of 3 is approximately y of 3, which is this y, right? Not the original one. I should be calling it L, because we are going to rename this. L of 3, and that is 3 over e. Well, wasn't that 3 divided by 2.7? Multiply both by 10, that's 30 over 27. Cancel by 3, you get 10 over 9. And that's about 1.111111 if you do your division in a sand. So what we calculated here by hand is that ln 3 is approximately 1.111111. Now you take your abacus, push ln, push 3 to check, and it says ln 3 is approximately 1.0986. Well, that 6 is going to make 8 into a 9, and that 9 is going to be making 9 into, right, a 10 over there. Wow. Like we're like 1 cent off. And have we done any hard calculations? No. So this is how they came up with all of the trig values and all of the, can you do sine of 3 degrees? Yeah. Right? You can do sine of 3 degrees. And tangent of, how you do tangent of, I don't know, 25 degrees. Tangent of 25 degrees is only 5 degrees away from tangent of 30 degrees. Make a footnote there. If you see any trig, you have to convert everything to radians. You cannot compute in degrees this will fail miserably if you try to compute in degrees. Mathematics only calculates in radians. All our formulas, the arc length, everything else, it's just radians, radians, radians. So you have to convert 5 degrees using conversion 180 is pi. You have to convert that into radians and then go from there, right? But it's possible to do all of those calculations. You can come up yourself, right? And you can go and write that book, right? You know that ln of 1 is 0. Okay, next one. ln of 1.1. ln of 1.2. ln of 1.2. Just keep doing these calculations over and over and over again. Who had that time to come up with the book?
Probably made bank though, selling that book.
Yeah,
I'm sure a lot of people are willing.
A lot of people, but who are those people?
Illuminati, dude. Come on, dude. It's out there already, dude.
Usually, people that had the knowledge to do this and had the time to do this were captains of ships. Because if you're on the sea for like 2-3 months to go between, Europe and US or something like that, right? you keep calculating. It's just so much of execution and stuff that you can do in one day. So, it's a ship. So now we are going to write a single equation which is going to calculate the tangent line. So far, we have the procedure for the tangent line. Calculate the derivative, find m, find y, right, and do all of those kind of things. But now, I'm going to tell you that L of x is equal to f of a plus f prime of a times x minus a. This is the linearization formula. This is the tangent line formula in one shot. Now, this might remind you of the formula y minus y1 is equal to mx minus x1. And yeah, that's exactly that formula, where your x1 is a and y1 is f of a. And you move it to the right side. And your slope, it's derivative computed at the value a. So that's that formula written in a calculus way to calculate. So this is called linearization. And what this is the tangent line in one formula. So the tangent line at x equals a. So if I am to go back and review my square root of 10, I will calculate L of x by f of 9 plus f prime of 9 times x minus 9. Same problem done up there in fragments is now done in one line. Now I know my f of x is root x, right? So we know that. So I have L of x is equal to square root of 9 plus 1 over 2 square root of 9 times x minus 9, which is 3 plus 1 over 6 x minus 9. Now you can calculate the y equal mx plus b form if you care, but the square root of 10 is now approximated by L of 10, which is 3 plus 1 over 6, 10 minus 9. And you get the same value, which was 3.166 going on forever. So this is you figuring out the tangent line in one formula rather than full procedure. Completely obsolete today. because of the calculators and computers, but you can use it to annoy the hell out of other people. Because as soon as they say, what do you know? I know the formula for tangent line in one shot, and you can't even spell it. So that's linearization, guys. Your job is to find the linear line, which is called tangent line, and compute the value in the tangent line rather than original calculation. You have your ln, you have your trig, you have your square roots or cube roots. You can take derivatives of all of those, right? And the only thing you have to be very careful about and think a lot about is to find that sweet value. In this case was 9 because I was looking for root 10. If I want to use square root of 79.7, what value am I using for a? In a square root? 81. 81 is the closest perfect square root to 79.7, right? And you would use 81 because square root of 81 is 9. So the hardest part is to figure it out. And obviously the hardest part is to figure out what is the great value when you have ln around. So what you can do is you can go on your calculator, right, and kind of take a look at what is e, 2.7, e squared, e cubed, e to the 4th, e to the 5th, just to see those numbers, right? And then you will be picking the closest, right, e to the whatever power, closest to the number you get to find ln of. And yeah, sometimes you are going to be off a couple of decimals, right? But sometimes you will be correct for the first 2 or 3 decimals, right? Depends on how close the value you can compute by hand is to the value that they are asking you to compute. So the closer they are, the less of the error. So that was a part 1 of the lecture. In the last 20 minutes, we are going to talk about the differentials. So differentials are really cool. They are going to give rise to integration and other stuff, differential equations, separation of variables, and so on. But for now, we are going to write 2 different notations. You know how y equals f of x, that's your pre-calc 1. So dy dx equals f prime. And now you are going to take dx and ship that to the right-hand side to get dy equals f prime dx. This equation here is called differential. Now, we all understand what f prime of x is, but what are now these dy and dx when you separate them like this, right? Well, in x. And it's a simple subtraction of 2 values. And we know that delta x is the same as dx. So I am boxing that red. Now, delta y is y2 minus y1, which is actually f of x2 minus f of x1. And that is change in y. Change in y. And I'll put, you know what? I'll put the word exact. Because dy is not the same as delta y, but they are close. Ha! What we figured here is that differentials approximate the change. So linearization approximates values, differentials approximate change. So now I can write delta y is approximated by dy, which is f prime of x delta x. And that one was supposed to be red and on the blue cloud. No, red. There we go. And on the blue cloud. So now I am going to say over here, differentials approximate the change in y. What was one of the main goals of calculus? To calculate change, to detect change, right? You change your position, you change your velocity. The change in velocity is acceleration. The change in position is velocity. You are detecting the change, and this one approximates the change. So if you take the derivative, that's exact. If you take the slope, that's exact. But in some cases, it's easier to compute the change than to compute the actual change. Right? It's easier to approximate the change than to compute the exact change. So let's take a look at an example of this problem. And we can just do a whole bunch of applied problems. So let's say approximate the change in volume of the ice cube as it is melting and we're just gonna look at the formula. I'll pick up the problems from the book, for example. So I'll just say formula, because no numbers are given. Okay, well, what do I have? I have an ice cube. I know that all sides of the cube are A, so the volume is A cubed. So now I am going to find the volume, the derivative, and then I'm going to move dA to the other side. Now this dA, we know it's equal to delta x. Now if you have ice cube melting, and let's say your ice cube was 1 inch by 1 inch, you can say that ice cube was 1 inch, and then you waited some time, and then A2 is 0.89 inch. So how much is your delta x, which is dA? It's going to be 0.9, started at 1 inch. So the change in volume is approximated by 3 times 1 squared times negative 0.11. And you can compute that as negative 0.33 inches squared. Cubed. Volume. Inches cubed. So that's the change in volume. And this is approximating the change. Is this the exact change? No. right? Now, this problem is not too complicated. So that's 1 minus 0.89 cubed. My change was 0.33. It should be negative because we are losing, I did this wrong. We are losing volume. So the negative sign should be there to signify that we are losing volume. I just did it backwards because I'm not thinking. So we don't have to calculate the change completely. Now, is it important to calculate this type of change? Yeah. A lot of design, for you mechanical engineers especially, is going to depend on these types of calculations. What happens in the extreme heat? Things expand. What happens when you cool them down rapidly? They contract, right? Why is there a sag on the electrical cables that you see as you drive out between those towers? Why is there a sag?
Change the temperature.
Change the temperature. The wires warm up, right? But what happens in the extreme cold? When you have a little bit of rain and then it freezes around the wires. Well, that's going to make them cold and they shrink. But when you have a cord that it's hanging, what happens when you make it shorter but these 2 points are still? It tightens up. So if they stretch it like this and have it tight between the two towers, and then the cold weather and icing hits, it either snaps or it rips out the tower out of the ground. All right? So they introduced a sag. Now, can they introduce too much sag? No, because every truck is going to hit it, right? Passing underneath. So these things have to be computed, and by the properties of materials, we know exactly how much they expand with certain heat. And that little expansion is change in delta L, the length of the cord. And that will introduce extra, right? So the computing the height of the tower and the sag of the wire, like all of these things are important. Another example would be train tracks. Do you know when you travel on the train tracks and there is always that sound, tick, 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 tick? What is making that sound? Is it broken train? Because every train I was on in the last 40 years did that.
It's the metal, right? Is it between the cars?
Nope.
The metal between the little space between each of the rails?
Yes. Rails are very long, and they're bolted onto those wood planks, right, that are parallel. So the rails are very long and not that thick, right? So when there is heat in the summer, right, and they bake in the sun, the only way they expand is lengthwise. If you don't have a gap pre-measured in there, if you put one next to the other and then they start expanding, they are going to bulge up and pop out. Go on the Google the pictures before they started putting those in to see the rails popped out and curled up, right? You have to introduce that. So now, in the winter, if you take the train now to the city, you will hear the tuck, 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 tuck a lot, and it will be really, right, loud. In the summer, you can barely hear it. You also know that when you drive over the bridge, right, there is that gap that you look down and you see, right? Especially those huge bridges that connect New Jersey and New York, right? And the bridge would have the zigzag like this, right? It's the same deal. The bridge will expand because, right, heats up. And when it expands, those gaps close. When it's winter, those gaps open. Obviously, they don't open like 10 feet apart. This is where the engineers such as you come in, right, and you compute these things. What else? CD players in a car. They used to have those. The CD is a disc that used to carry music on it.
What?
Yeah, it's a disc like about this big, and it had
Spotify. What is that?
That's okay, but it looks like a Blu-ray. It looks the same as a Blu-ray.
Is that like Netflix? What's going on with this?
I can't win on that one. So when you put the CD player, and I'm picking on a car, you put the CD player, right, CD into CD player in a car, it's going to spin with whatever angular velocity omega, which is revolutions per minute. And you are going to have a linear track underneath the disk that has a little metal head, right, that has a laser on it. That laser will shoot at the disk, bounce off the signal, collect the signal, and read the data off of the disk, and then convert that into whatever, right, music you have in there, right? So what happens to the disk as you shoot the laser into it? It expands, right? And how precise are these tracks and data on the laser red disk? Very precise, right? So if your electronics doesn't have a temperature probe, and these things are not computed properly and designed properly, right, you won't be able to hear any of it, right? Because it will be just skipping around. So you have to, right, take in consideration all of these. You have to take in consideration all of these changes, and for, as you can see, many of them, right, it's easier to compute differential than to compute the actual expansion and all of that. So you can use this to your advantage. Do we have time for? Yes, we do have time for one more example of differentials. All of these are. And you can use differentials to approximate values of numbers as well. Remember, differentials approximate change. So you can use it not directly, you can use it indirectly to calculate, let's say, square root of 10, right? So let's calculate square root of 10 using differentials. Square root of 10 using differentials. And you will see it's completely different. So you know how to do this using a tangent line. Now, using differentials, you have your f of x is equal to, very good. And your value that you can easily calculate is 9, but then you want to go to 10, because 10 is what you care about. 9 is what you can compute, but 10 is what you care about. So your delta x is 10 minus 9, which is 1. Right? Now you have your change in y approximated by dy, which is f prime at 9 times delta x. That's your differential formula. Now, what is your f prime? It's 1 over 2 square root of 9 times 1. And that is good old 1 over. So what is the square root of 10? Square root of 10 is approximately square root of 9 plus 1 over 6. Okay? That's what it is. And how much is that? That's 3 plus 0.166, which is 3.166 going on. Now, did we calculate this directly? No, right? we calculated with the differential the change that is introduced in y by going from 10 to 9. That's what we calculated with differential. We did not calculate the value. We calculated the change only, and we said what I can compute plus or minus the change, depending on which way you need to go, right? You add the change onto what you can compute without a calculator to come up with the approximated value at the end. So you can use differentials to compute numbers as well. One of the cool problems that generally talk about, and since we only have a minute and a half, I can skip on it, is the ideal gas formula. And it's cool to think about that one with this topic, because you know that we all have to do Mario Kart around the exploded tires on the highway, right? So what is that all about, right? And why is there so many of those tires explode in the summer and not so many now? Well, what's the difference between now and summer?
Super hot.
Heat. So you already have the heat, which is friction, rubber against the road, the asphalt. It needs to produce that heat because you need friction, otherwise, right? It's ice skating. So friction is the one that keeps your car on the road, which is why you want a good tread on your tire. You do not want rain, you do not want ice, you do not want wet leaves or oil, right? When it spills on the highway, because you need as much friction to keep your car on the road. So there is friction already, introduces heat. But now you have added 100 degrees of the weather effect, right? Now, what is constant? Volume is constant. If you don't lower your tire pressure, the change in temperature is enough for, right? Which is why, right, this concept here explains why you have to have lower pressure in your tires during the summer and higher pressure in your tires now when it's colder outside, right? And when truck drivers, right, fail to check one of the tires or adjust one of the tires for the summer conditions, right, you get to do the thing around, right? And those explosions, if you're next to them, they are not fun. If anyone ever experienced, they are terrifying.
I was on the way down to Florida and I watched it happen.
Yeah.
I saw one
I
coming
don't
on.
understand.
So, all right.